Okay, welcome to lecture 10.1 on stability. Now, I want to say right away that we're going to look at two different notions of stability, different but closely related in this lecture. So it's important to keep them separate in your minds. One is the stability of a transfer function, and the other is the stability of the system that might be represented by that transfer function. So these are going to be closely related, but slightly different. That's something to keep in mind. Let's start maybe with a bit of a recap of what we've done recently in analyzing the time domain responses of LTI systems. We've been studying in particular the relationship between the forms of the time domain responses, specifically the impulse response and the step response, and the locations of the poles and zeros of the transfer function on the S-plane. So we looked, for instance, first of all, at the example of a standard first-order system, which showed us the effect of real poles on the time domain response. We saw that if we have a single real pole, then the impulse response is going to have the form of a decaying exponential, which is what this plot is meant to represent. We also saw that the closer that pole gets to the imaginary axis, the slower that exponential decays. So the response becomes slower as we approach the imaginary axis. In particular, the time it takes for the transient part of the response to decay away gets slower as the pole gets closer to the imaginary axis. We also looked at the example of the standard second-order system, which, for the underdamped case, showed us the effect of complex poles on the response. And there we saw that if we have complex poles that lie to the left of the imaginary axis, the impulse response has the form of a damped sinusoid. And the step response, of course, is the integral of that impulse response. Again, this is a damped sinusoid, so in this case it's the amplitude of the oscillations that decays exponentially. And again, as you get closer to the imaginary axis, that decay happens more and more slowly. In particular, when you get to a pole that's right on the imaginary axis, which is the undamped case, which we didn't really look at explicitly, but this is the case where zeta becomes equal to 0. In that case, it's easy to see that the impulse response is simply an undamped sinusoid. It's an ordinary sinusoid of constant amplitude. So the decay in the amplitude gets slower and slower as the pole gets closer and closer to the imaginary axis. And if it's right on the imaginary axis, we have an undamped sinusoid. The frequency of the oscillations is given by the imaginary part of the pole. So if we consider these two undamped examples, in this case, the pole is further from the origin, so the frequency of oscillation is higher than in this case, because again, the angular frequency of oscillation is given by the imaginary part of the poles. We also, of course, looked at the responses of systems with more complicated transfer functions, and we saw that in a case where we have a higher order transfer function that has more than two poles, we can use partial fractions decomposition to decompose it into the case of a number of simpler systems of the forms of our first and second order systems. So in fact, we're really associating a certain kind of response with the different poles that we have in our transfer function. And if we have a large number of poles, we know we're going to get different responses of these different forms associated with the various poles. We also saw that as one pole gets much further away from the imaginary axis than the other poles, then eventually its contribution, at least when you look at the transient response, its contribution is going to become negligible. And as far as transients are concerned, you can ignore that pole. We also looked at the effect of zeros, and we saw that they essentially introduce derivatives of the response. So if we were looking at the step response, then zeros would introduce additional terms proportional to the impulse response. And there again, the effect of these zeros lessened as the zero moved further away from the imaginary axis in comparison with the poles. And in fact, when an engineer is thinking about the response of a system, he or she typically will not actually compute the response in the time domain. They can simply look at the pole zero diagram of the transfer function, see where the poles and zeros lie, and that gives them immediately a pretty good idea of the form of the response of the system. So that's the real point of this part of the course that we've just gone through. It's to learn the effects of different poles and zeros and their locations on the overall response of a system. That's useful even if you don't go through the exercise of computing the response exactly. Now, in the examples that we looked at, the real parts of the poles were always strictly negative. So any real exponential factors that appeared in our responses were decaying exponential factors. If you move to the right-hand side of the imaginary axis, then those decaying exponentials become growing exponentials. So the impulse response sort of blows up exponentially with time. And as we just discussed, if a pole lies right on the imaginary axis, then you have neither a growing nor a decaying exponential. You just have a constant factor. So if you have a non-zero imaginary pole, that corresponds to an undamped oscillation. If you have, say, a single pole at the origin, that corresponds to an impulse response that has the form of a step, a unit step. But you only get decaying impulse responses if the poles all lie in the left half plane. And in that case, we're going to say that the transfer function is stable. Any transients that arise when you excite the system with an impulse decay away as time goes to infinity. That is not the case if the poles lie on the imaginary axis or to its right. If they're on the imaginary axis, you don't get any decay. If they're to the right of the imaginary axis, you get exponential growth. So, as I said, we're going to say that a transfer function, and so this is the first kind of stability that we're talking about, we'll say that a transfer function is stable if all of its poles lie strictly to the left of the imaginary axis. And we've got that written down here. A rational transfer function is stable if all of its poles lie strictly to the left of the imaginary axis. In other words, they all have real parts that are strictly negative. So the intuition again is quite simply that in that case, all of the terms in the impulse response corresponding to the respective poles are all going to contain decaying exponential factors, and they're all going to decay to zero as time goes to infinity. So that's what we mean by the stability of a transfer function, but we're going to use that notion of stability of a transfer function to come up with a somewhat stronger stability that relates to systems. Now, what's the difference? I mean, in this course, we're mainly using transfer functions as our principal model of systems. But recall what the basic definition of a system is. A system is a mapping from a space of input signals to output signals. And our notion of stability that we apply to systems is going to recognize that fact. It's going to depend on the notion of the boundedness of a signal. Essentially, what we're going to say is that a system is stable in the bounded input, bounded output sense if whenever the input signal is bounded, the output signal is also bounded. So what do we mean by that? Let's take the case of a real valued signal, just because it's easier to draw pictures. So we say that a signal x of t is bounded if there exists some real number m such that the absolute value of x of t is less than or equal to that constant real number m for all values of t. So the picture would look like this. Here we've got, say, a two-sided function x of t. Same definition applies, of course, to one-sided functions. And the definition simply means that the value of x of t, for the case of a real valued signal, lies between minus m and plus m all the time. So we say that such a signal is bounded. And of course this definition can be applied to complex valued signals as well. In that case, the role of the absolute value is played by the modulus, but it's the same idea. So again, a system being a map from a space of input signals to a space of output signals, we're going to define our notion of stability for systems in terms of signals. And in particular, we will say that a single input, single output, linear time invariant system with a rational transfer function is bounded input, bounded output stable if its zero state response is bounded whenever the input is. I didn't have to throw in with a rational transfer function there, but you'll see that we use our definition of stability of transfer functions in characterizing BIBO stability. So if we look specifically at the examples of the standard first and second order systems, those systems are BIBO stable whenever the transfer functions are stable. And in fact, we assumed that all of the parameters in our examples were positive, so those examples did always have stable transfer functions. You know, the poles lay to the left of the imaginary axis. So those were examples of stable transfer functions. It turns out, in fact, that those examples were also stable in the bounded input, bounded output sense. And we'll see why in a moment. In order to see why, it's useful to consider some non-examples, if you like. Some systems that are not bounded input, bounded output stable. And two handy examples are those of an integrator and a differentiator. So what's the transfer function of a differentiator? Well, we're always interested here, in this case, in zero state responses. If you just have a differential equation and you don't specify what the values of the initial conditions are, then in a sense you don't really have a system, because recall that by a system we meant a mapping that maps every possible input signal to a unique output signal. Now if the initial conditions are not satisfied, you don't have that, are not specified, then you don't have that uniqueness. For a given input signal there could be many different output signals depending on the values of the initial conditions. So to avoid that ambiguity, we are almost always talking about zero state response when we talk about systems. So the initial conditions are all zero. So we know from the integration and differentiation property of the Laplace transform that when the initial conditions are zero valued, integration in the time domain corresponds to multiplying by 1 over s in the Laplace domain. So the transfer function of an integrator is 1 over s. If you feed in an input signal u to a system whose transfer function is 1 over s, the output y is just going to be the integral of u. This is the reason why, for instance, the step response of a system is the integral of the impulse response. To get the step response, instead of multiplying the transfer function by 1, as you do to find the impulse response, you multiply the transfer function by 1 over s, the transform of a unit step. But multiplying by 1 over s is the same thing as integrating. So that's why the step response is the integral of the impulse response. So why would we consider this to be a system that is not, because this is a non-example, not BIBO stable? It's not bounded input, bounded output stable. If that is so, then there must be a bounded input u for which the unique corresponding output y is unbounded. Maybe you want to take a moment to see whether you can think of an example of a bounded input u that gives rise to an unbounded output y. Well, one simple example would be a step input. If the input is the form of a step, suppose it's a unit step for simplicity, then we can set m equal to 1 in the definition of boundedness, and that step is a bounded signal. But what's the integral of a step? The integral of a step is a ramp which goes on growing and therefore cannot be bounded. You can choose any m, and at some time the ramp input is going to exceed that value of m, or its absolute value is going to exceed that value of m. So if you feed a bounded step input into an integrator, you get an unbounded ramp. Therefore, an integrator is not a bounded input, bounded output signal. And bounded input, bounded output stability is useful in a practical sense. Obviously, it's not a very strong assumption to assume that signals remain bounded, but it's kind of a minimal assumption that we need for practicality in a lot of examples. It's hard to deal with signals that grow without bound. So in a bounded input, bounded output stable system, we know that as long as the input that we feed in is bounded, the output will remain bounded, and that's a useful notion of stability. But it's a notion of stability that the integrator itself does not satisfy. What about the inverse system, if you like? What about a differentiator? Well, in this case, you can probably also think of an example of a bounded input u that gives rise to an unbounded output y. In fact, in this case, you can use the same example. If you feed a step into a differentiator, well, strictly speaking, a step isn't differentiable. It doesn't have a derivative. But if you look at the formulation of our integration and differentiation property for the Laplace transform, you know that we can let the generalized function, the unit impulse, serve as a kind of derivative of the unit step. And in fact, if we take the transform 1 over s of a unit step, multiply it by s, which multiplication by s in the Laplace domain corresponds to differentiation in the time domain. If we carry out that multiplication, we get 1, which is the transform of the impulse. So if we feed a unit step into a differentiator, we get an impulse, and an impulse function obviously cannot be bounded. You can think of it as an infinitely high but infinitely narrow spike, so it's not a bounded function. So neither an integrator nor a differentiator is a bounded input, bounded output system. And again, in both cases, you can see that by thinking about their step responses for both these examples. So how do we know when a system is bounded input, bounded output stable? Well, it turns out there's a very simple condition. And in fact, those two non-examples illustrate the different ways in which this condition can be violated. A SISO LTI system is bibostable if and only if its transfer function is both stable and proper. Okay. So let's go back to our non-examples. In the first case, we can see that the transfer function of the integrator does not satisfy our definition of stability of the transfer function. It has a single pole, and that pole lies at the origin, so it's right on the imaginary axis instead of being strictly to the left of it. So this example is an example of a system whose transfer function is unstable. And just as we said, if you can feed in a step and the output will grow without bound. So it's not bibostable. What about the differentiator? In the case of the differentiator, the transfer function doesn't have any poles, so it has to be considered stable. Stability is a condition on all of the poles of a transfer function. In this case, it's satisfied vacuously because there aren't any poles. However, this transfer function is not proper. If we view this as a rational transfer function, if you like, it's s over 1. So the degree of the numerator is 1. The numerator polynomial is the first degree. The denominator polynomial is just a constant, so it's a 0th degree, if you like. So the degree of the numerator is greater than that of the denominator. That means this is not a proper function. It's an improper function. And according to the theorem, that explains why this system is not bibostable. So these are kind of key examples, and they will help us follow the proof sketch for this result. So we're going to prove that a single input, single output LTI system is bounded input, bounded output stable if and only if its transfer function is both stable and proper. So if the transfer function is, let's prove the if part. In other words, let's show that this condition that the transfer function is both stable and proper is a sufficient condition for bounded input, bounded output stability. In other words, if the transfer function is both stable and proper, the system is bibostable. Well, for that we just suppose that the transfer function is both stable and proper. We can then use our usual technique and apply partial fractions decomposition. In that case, it can be decomposed into, well, terms of this form, which are standard ones that we get in a partial fractions decomposition, where p sub I is one of the poles of the transfer function. But as you've seen, if it is proper but not strictly proper, then you may need to include a constant term. Let's say a naught. Okay, so if h of s is stable and proper, it can be decomposed into a constant term a naught plus a number of terms of this form where the pi's are poles of the transfer function. And because the transfer function is stable, the real parts of those poles are all strictly less than 0. Well, if we take the inverse transform of a term of this form, what we get is t to the power k times an exponential e to the pi t times the unit step. I'm assuming here that these are transforms of one-sided functions. So in other words, their regions of convergence are right half planes. For whenever the real part of S is sufficiently large, the transform converges. In that case, when we invert the transform, we get a one-sided function like this that consists of t raised to the power k times an exponential e to the pi t. And because the real part of pi is negative, that means that the real exponential that results from the real part of pi is going to be a decaying exponential. What about the constant a naught term? We know what we get when we invert this. When we invert a naught, what do we get? Well, a naught being just a constant, we get an impulse. So we get a term a naught times a unit impulse from the constant term, and we get, in terms of tau instead of t, we get tau to the k times e to the pi tau for all of the other terms that correspond to non-zero poles. That correspond to poles which lie to the left of the imaginary axis. Now, what happens when we perform this convolution? We know that we have to, what we get when we invert the transfer function is the impulse response. In order to find the response of the system, we have to convolve that impulse response with our input, say u. So here's a convolution of u with the first term, if you like, the term that results from the first term in our partial fractions decomposition, from the constant term a naught. We can divide the convolution up into these convolutions with different terms just because convolution is a linear operation. So let's first convolve our input with this a naught times an impulse that we get from the constant term in our partial fractions decomposition. Well, we know by the sifting property that this is that the integral of u of t minus tau times delta tau will just give us u of t. And we're assuming here that the input signal u of t is bounded. So its absolute value is bounded by m. So u of t is less than or equal to m. That's going to get multiplied by this constant a naught, but that's not a problem. We know that the convolution, therefore, is bounded by the value m times a naught. So taking this convolution gives us a bounded function. So as far as the first term in our partial fractions decomposition goes, we're all right. The same is true of the other terms in our partial fractions decomposition because our transfer function is stable. So the real parts of the poles pi are strictly negative. That means that this term looks like a decaying exponential, a decaying real exponential, possibly multiplied by a complex exponential, a term like e to the j omega tau, which represents essentially a sinusoid. The important thing is that the real part, the real exponential factor, is a decaying one. So that means that the modulus of this term is going to decay to 0 as tau goes to infinity. Well, again, we're assuming that our input u is bounded by the value m. So this being positive, we know that this u of t minus tau is going to be less than or equal to m by its boundedness. Therefore, we know that that integral is going to be less than or equal to m times the integral of the rest of the integrand, the tau to the k e to the pi tau d tau term. But if, again, the real part of pi is negative, this contains a factor that is a real factor that is a decaying exponential, possibly multiplied by a sinusoid. But by virtue of the fact that we have this decaying real exponential, this integral will converge. So that means that this convolution is also a bounded function. This integral is just going to give us a constant. So when we convolve our bounded input with any of the terms in our impulse response, whether they result from the constant term in the partial fractions decomposition or from the other terms corresponding to poles of the transfer function, they're going to give us bounded functions. The convolutions will be bounded functions. Therefore, the sum of this finite number of bounded convolutions is also bounded. So whatever the bounded input u that you feed into your system, the output, which is the convolution of that input with the impulse response, is going to be bounded. So if your transfer function is both stable and proper, then the system is going to be stable in the bounded input, bounded output sense. So that completes the if part of the proof. If. What's the only if? The only if part is that a SISO-LTI system with rational transfer function is bibostable if and only if its transfer function is both stable and proper. So in this case, we assume bibostability. We have to prove that the transfer function is stable and that it is proper. So let's suppose, first of all, that the system is bibostable, but the transfer function is unstable. If the transfer function is unstable, what does that mean? That means it has a pole whose real part is non-negative. It's greater than or equal to 0. Now, we know that if the real part of p is greater than 0, then, for instance, the step response includes an increasing exponential term. In fact, the impulse response also includes an increasing exponential term, but that means that the step response does, and that is the point here, because a step, once again, is a bounded input. So if we feed in a bounded step input, we're going to get, as one term in our response at least, an increasing exponential. So the output is going to be unbounded. So that takes care of the case where the real part of p is greater than 0, where the transfer function has a pole that is strictly to the right of the imaginary axis. If the pole is equal to 0, so if the pole is right at the origin, then we know that the impulse response is going to be a step, and therefore the step response is going to be a ramp. So this is exactly the case of our integrator. We looked at the integrator example and saw that its step response is a ramp. Therefore, it is not stable in the bounded input, bounded output sense, a step being bounded and a ramp being unbounded. So if p is right at the origin, if the pole p is right at the origin, then the step response includes a ramp. So we've covered the case where the pole is to the right of the imaginary axis, or where it is on the imaginary axis and right at the origin. So what if it is on the imaginary axis but not at the origin? So let's suppose it's equal to j omega for some non-zero omega. Then if the input to the system is, say, e to the j omega t, so this is essentially a sinusoid. It's just convenient to make it a complex sinusoid for mathematical simplicity. So let the input be this bounded function, e to the j omega t, which is just a sinusoid. Then it's easy to see that the output, the transform of the output, is going to contain a term of the form 1 over s minus j omega all squared. And that means that when you invert that term, you're going to get a term in the response of the system to this bounded sinusoidal input that looks like t times the same bounded sinusoidal input. So if there is a pole that gives you, if you like, in the impulse response, a sinusoidal response of constant amplitude, then if you excite the system at the corresponding frequency by feeding in an input that is the same sinusoid, then you're going to get a sinusoid at that frequency that's multiplied by t. So its amplitude grows without bound. So that shows that if you have a pole that lies right on the imaginary axis but is non-zero, then a bounded input can give you an unbounded output. This covers all of the cases of an unstable transfer function, case where there's a pole that lies to the right of the imaginary axis, and the case where there's a pole that lies on the imaginary axis either at the origin or elsewhere. And it shows that in all such cases, your system will not be bounded input, bounded output stable. In all those cases, there exists a bounded input that gives rise to a bounded output. So for Bibo stability, the transfer function must be stable. Your system is Bibo stable only if the transfer function is stable. But we also need to show that the transfer function is, that the system rather, is Bibo stable only if the transfer function is proper. So let's suppose that's not the case. Suppose the transfer function is stable but it's not proper. If that's the case, then we can decompose the transfer function h of s this way. We can have a term n over s n of s over d of s. And let's suppose that this is a strictly proper term. Then we'll need to add to that a function q of s, where q of s is a polynomial that is not just a constant. If it were just a constant, then h of s would be proper, but not strictly proper. But we're assuming here that h of s is improper. That means you get a term like s, or s squared, or higher order, higher degrees of s. Okay, so Q is non-constant here, and D, of course, is a non-zero polynomial. And we can assume that n of s over d of s is strictly proper. Now, what if the input is a step? Again, let's use a step. It's a convenient example of a bounded input, and see what we get. Well, we'll get, in the transform of the response, we'll get 1 over s times this strictly proper term, n of s over d of s. And that's not a problem, but we will also get another term that consists of 1 over s multiplied by q of s. Okay, so this is going to include either a unit impulse, delta of t, corresponding to the case where q of s contains a term in s, for instance. If q of s were equal to s, for instance, as in the case of our differentiator, then we would be taking the Laplace transform of s times 1 over s, which is 1, and of course the inverse transform is an impulse. Just as in our example of a differentiator, we found that when we fed into the differentiator a step input, we got an impulse as the output. So our bounded step input gave rise to an unbounded impulse at the output. We don't necessarily have terms in S here. We could have higher order terms in S, which correspond to what are called derivatives of unit impulses, and there again you have an unbounded signal in that case. So as long as we have this non-constant polynomial q of s, which we will have if the transfer function is improper, then when we feed in a step input, we will get an unbounded response. So this proves that not only must the transfer function h be stable for bibostability, it must also be proper. And in this example, in this last example, we were essentially generalizing from the example of a differentiator. We saw that it was an example of an improper but stable transfer function, but it represented a system that was not bibostable, in particular because its step response was an impulse, which is unbounded. So that's a quick discussion of stability. And this will be useful in our next topic, which is so-called frequency response. So just to recap, we defined two notions of stability. One was stability of a transfer function, and the second was stability of systems. We said a transfer function was stable if all of its poles lay to the left, strictly to the left of the imaginary axis. So all of the real parts of all of its poles were strictly negative. And we've just seen that a system is stable in the sense that every bounded input gives rise to a bounded output. So bounded input, bounded output stable, if and only if its transfer function is stable and, in addition, its transfer function is proper. So that ends this lecture, and we'll go on and use this notion of stability in our next topic, where we're going to leave the time domain and go to what we call the frequency domain, an example of the frequency domain. In particular, we'll look at the responses of stable systems to inputs in the form of sinusoids. See that in the next lecture.